Okay, I can see that people are streaming into our virtual room, so I'm going to get started. A very warm welcome to you all and to the new session of meetings. And we are delighted to bring you the first meeting of the 2020-2021 session via webinar. And it's just great that so many of you can join us for this new experience of the RAS ordinary meetings online. Okay, without further ado then, we will begin the programme for this meeting. So in today's meeting, we're going to hear this year's George Darwin lecture, and this is going to be given by Professor Ofer Lahav from University College London. And Professor Ofer Lahav is Perrin Chair of Astronomy at UCL, and his research area of expertise is observational cosmology, and in particular probing and characterizing dark matter and dark energy. And he's also an expert in machine learning methods within his research, and he's currently co-directing the Centre for Doctoral Training in Data Intensive Science. And today Ofer is going to talk about both these aspects as he presents the George Darwin lecture entitled Darkness Visible, AI in Cosmological Experiments. So I'm going to hand over to you, Ofer, to take the stage. Thank you very much.
Thank you very much, Emma, for the kind introduction. Thanks to the RAS for inviting me to give this George Darwin lecture. And thanks for those who are on the line. Unfortunately, I cannot see you, but thanks very much for joining at the end of a week where you probably had many Zooming hours. So I will share the screen now, if that's okay. And I'll put it on full screen. Can you see it all right, Emma?
Yes, that's fine. Looks good.
Okay, very good. So as mentioned, the topic is darkness visible, AI in cosmological experiments. But actually, I think most of you know what AI normally stands for. Actually, as I'll indicate, I'm thinking about something a little bit different than artificial intelligence. So I hope you won't ask for the money back. The way I would like to organize it is by actually connecting those two disciplines, AI and cosmology, in the broader context. But first, as it is a lecture in honor of George Darwin, I looked a bit about his life and work. It's really fascinating. He was a barrister and astronomer. He was the Plumian professor in Cambridge. I believe there are two of his successors are on the line, Martin Rees and Richard Ellis. He was also president of the RAS, one of Emma's predecessors, and an FRS. His work was on the interaction of sun, earth, and moon, three bodies. And he had quite an original idea of how the moon formed. My colleagues who are experts in this tell me that his model is not so popular anymore, but still he developed interesting methods. He was the son of Charles and Emma Darwin. And interesting enough, apart from astronomy and apart from being a barrister, he also studied the health outcomes of first cousin marriages, which was something of great interest to the Darwin family. So I think we have an example here of interdisciplinarity and knowledge transfer. And although there was a period of people said, oh, people become so specialized, if anything, the message of this lecture, especially towards the end, is that data-intensive science, AI, etc., actually bring together different disciplines. And the same individual can work on many different fields at the same time. That's one message of this talk. The outline is I would like to review galaxy surveys, present and future, the status of the standard model of cosmology, so-called cold dark matter plus lambda, which has survived, depends how you count, when you count the birth of that model, but it's for at least 30 years. And then how AI machine learning is coming into it. And I would like to talk also about the training of the next generation of scientists in data science. So artificial intelligence in certain, there are some people who love it, some people who hate it. It's a bit like Mermite. It depends what what's your attitude? It sounds a bit mysterious. Some people are worried, it's all going to be taken over. We don't need people anymore. It's all going to be done by robots. Well, I'm going to take this approach, and this is this very schematic triangle I've drawn of connecting the AI to the laws of physics, which we've known for many hundreds of years, or to some of them, and to human knowledge, human experience. I think these three should be connected. And in fact, in certain circles, there's a new term where AI does not stand for artificial intelligence, but rather it stands for augmented intelligence. And I'm more and more convinced that that's the way to go, to generate tools which help the experts to make the most of the data. So that's another message of this talk, which you will see examples of. Now, astronomy is just flooded with data. We've been very fortunate. We're in a great period of astronomy. It may or may not continue this way due to all the other external problems we have in the world right now. But it's really quite remarkable that almost every technology project we're aware of got even funded in the past decade, and maybe two projects got merged together and got funded and so on. I think it's very remarkable. We've been a very successful community, of course, is also expressed by Nobel Prizes and so on, including this week. I think it's really a lot of, it's a very exciting period, I think, to continue working in the field and for young people to join the field. But this is just to show, I listed only 5 of projects, partially because UCL and other departments in the UK are involved in them. Dark Energy Survey, DESI, which is spectroscopic instrument, LSST, which was recently renamed after Vera Rubin, Euclid, ESA satellite, SKA square kilometer array. And I listed roughly the amount of data that would come every night or day, depends on the wavelength. And you can see it would run into the 1 peta bytes with SKA, dwarfing mobile phone traffic and so on. In terms of galaxies, when I was a PhD student in Cambridge, I was very proud to use a sample of 30,000 galaxies. And now in DES, we've collected 300 million, and then we're moving into the billions. The cost also goes up from tens of millions of dollars to billions. I like to tell the funding agencies that it's a very good deal. If you do a project for $1 billion and you mapped billion galaxies, it's only $1 per galaxy. It's a fantastic bargain. The number of scientists goes up, and this leads to all kind of fascinating sociological aspects of how do you run a collaboration and how do you produce healthy interaction among hundreds of people. I think it's a new challenge, and we followed the footsteps of the particle physics in that area. So I think these are lots of things to think about, from the number of pixels to the number of people. So these are some images of those surveys. DES and DESI at the center. They're all telescopes which have sort of got good life, got sort of new life with great new instrumentation. And I'm pleased to see some of that instrumentation for both projects was actually assembled at UCL, the optical correctors, by my colleagues Peter Dole and David Brooks. But of course, with the work of many other people around the world. These are all international collaborations which involves tens of institutions. And on the right is the LSST, which they like to say it's going to be the movie of the universe, and Euclid, the space mission. And I know there are many people on the line who are involved in this, have been involved for many years, including students who just joined the PhD program this week, and they'll be working on this and see the fruits. DES already collected data. DESI started collecting data, but now is we have to wait a bit, hopefully for operation post, the slowdown due to COVID. LSST and Euclid are in construction, but people are talking about a couple of years to see them working. Obviously we all have our pet projects, and in my case, it's the Dark Energy Survey. I was very fortunate just after I moved from Cambridge to UCL in 2004, months later, at a random meeting in Paris, to talk to Fermilab people, John Peoples and Josh Freeman, and to get UCL and the UK involved in it. And in fact, STFC was the first to give money towards the project. It's a multi-probe approach, which has then been followed by other projects such as LSST and Euclid, of looking at clusters, weak lensing, large structure supernovae. I'll say a few words about each. We already got in the bag 300 million galaxies and thousands of supernovae. I've already mentioned the number of collaborators and observations finished in 2019. There are already over 250 papers, but the collaboration is very busy now analyzing data from the first 3 years and eventually from the first 6 years. I was very privileged to co-lead the science program, the science committee of this project until 2016. It's been a very interesting process of putting together working groups and see the preparations and then seeing the first papers. We actually felt that it's time to reflect about this. Projects are done. At the end, there are results in technical journals, but where is the story? Why have people decided to spend 10, 15 years of their life putting a satellite into orbit or doing a project on the ground? And we felt about 7 years ago that it would be quite interesting to actually have a book which documents the project in the words of the people who have actually created it. So there are 88 co-authors, and it was quite a challenge editing it, luckily with help with 3 other co-editors. But we end up with 27 chapters, and apart from dark energy and the construction and also non-dark energy science, there are also some reflections by a poet, philosopher, an artist, and an anthropologist. So I hope those who look at it may find it interesting. In fact, first, this is actually, here is the book, the actual book. I made it all the way from Singapore. And this is the telescope I refer to, the 4-meter Blanco telescope in Chile. For those of you who are not completely Zoom fatigued, we'll have a virtual book launch on coming Tuesday, 3 p.m. UK time. If anyone is interested, please drop me a line. Good. So what is this dark energy? Why would the society put so much money into it, and how come we encourage hundreds of people to work on it? Well, it's a fascinating concept. It goes back to lambda, cosmological constant, which Einstein introduced in 1917. This is the cover of his paper in German. And the here and now is that we think at present 70% or so of the universe is made of that substance. We don't know if it's exactly the cosmological constant, but it's something very close to it, where, as you know well, only 5% are atomic baryonic matter, and about 25% is in the form of cold dark matter, which is also still a mystery. And this dark energy is causing an acceleration, or some may say the observations show there's acceleration. We don't know what is causing it. A brief history here. This is Einstein's equation in full glory. He put lambda, by the way, on the left-hand side. Now, I think many cosmologists think it should be on the right-hand side as some kind of vacuum energy. If you take the weak field limit, there is the actual standard gravity, which I believe Newton developed in 1666 during the plague, when he had to be in quarantine in his village. But then there was also this additional term, linear in R, and here's lambda. It turns out actually Newton does mention a linear force in Principia. It's very surprising, and there have been some popular articles, including by us, written about this. Very surprising that he thought about that. There is a reason for it, which I don't have time to go into. But there's been controversy about the reality of lambda for many, many years. That's such a mystery. Einstein, of course, introduced it to get a static universe. The universe turned to be expanding, and he referred to it as the blunder of his life. But his good friend Eddington, another sort of Plumian professor actually, he said he was a detective in search for a criminal, lambda. And here are the two of them probably discussing lambda. I'm not quite sure what they said about lambda. at the grounds of the observatory in Cambridge, the Institute of Astronomy, currently in about 1930. It's just a simple diagram to say that you can generalize the concept and you can discuss some density which varies like this. When W is -1, exactly, you get a constant. That's Einstein constant. Now, what is this W? It's the so-called equation of state of the dark energy. It's pressure divided by density. So some people have reasons to believe W is exactly -1. That's a flat line here. Other people say it's deviation from that. And quite a lot of this effort is going into that, into explaining that. I should say the universe started accelerating about 6 gigayears ago. It's recent, but not that recent. You know, the solar system formed what, 4.5 gigayears ago. So the universe started accelerating before the solar system actually was formed. And how do we do it? We don't see lambda written on the sky. We have to do it indirectly. You can think of it as an inverse problem. We have standard candles. We don't have candles in the universe, but we have supernovae that do the job. Both in the galaxies and the CMB. This is here with some objects which get lensed, distant objects that get lensed by the gravity of the cluster. And we have weak gravitational lensing, where every object almost in the universe gets slightly distorted by a tiny amount. And we can take that distortion and work it backward and see what's the stuff in matter between us and the distant object. So that's a geometry, but the universe is also actually the structure grows, and that's also sensitive to the cosmological constant or dark energy. And here you can see what happens in 13.8 billion years. And gravity, for better or worse, it's an unfair force. It's really unfair. The rich gets richer, the poor gets poorer. Regions which are overdense become even denser. They bring together stuff nearby, and other regions which were underdense become voids. And people are interested in all these features. And so what do the data show? As you know, 2 supernova teams in 1998, 99, discovered the acceleration of the universe, won the Nobel Prize in 2011. And since then, many groups, including Dark Energy Survey, map supernovae. So this is what's called the distance modulus, or the magnitude of the supernovae in some normalization against the redshift. And the model we knew, at least when I was a PhD student in Cambridge in the late 80s, which was believed to be that line. Hopefully you can see the cursor, the blue dashed line, which is now completely ruled out. This was used Einstein, the city universe, without lambda, and omega m of 1 is now out. And now it's this model. You see W and omega matter. Omega matter is this 30% or so, which is the sum of cold dark matter and baryonic matter, and -1 is the dark energy parameter equation of state, which is -1 to 6%. That's the story, but LCDM is done pretty well for 30 years, but there are tensions. And there's a debate in this community. There are some practitioners on the line, others maybe are outside the field. There's tension, and I have to be quite careful how I present it because there are different camps. And for example, the Hubble constant in one camp, cosmic ladder, is only 74 in these units of kilometer per second per megaparsec. In another camp from the CMB, it's 67 or so. So what's going on here? We don't quite know. Is it new physics or some systematics? There's a new technique called using gravitational wave sirens, bright sirens, dark sirens. There's no time to go through it, but many groups around the world work on it, including in our little corner. This is an H0 from a paper led by my current PhD student, Konstantina Nicolaou, and there's another value using dark and bright by Antonella Palmazzi, a postdoc at Fermilab and previously a student of mine. There's also a dispute about the amount of clumpiness on the universe. You've seen how clumpiness evolves. There's some dispute between weak lensing and cosmic micro background about 2 sigma. I refer you to excellent papers recently produced by the KIDS team and the EBOS team. So that's the state of cosmology. So you can take a little pause. We're told when we teach after 15 minutes to have a little pause. So take a little pause, but not for too long, and just switch your mind from the mainstream cosmology and all these issues into the topic of AI, which you may think artificial intelligence. I like to say augmented intelligence. So again, some people like it, some people are very suspicious of it. I've seen a phrase that people say, would managers in industry be replaced by robots? The answer is not, but managers who have good command of AI will probably get the jobs. So I think this is the message. I think these are tools we all need. And the question is AI, or ML stands for machine learning, is it just a black box? Can we explain or interpret? These are two definitions of, or approaches to understand what's going on. How do we minimize biases due to incomplete training sets? If I only train a computer by only showing dogs, I don't think there's a way this computer can easily discover cats. And even if I put the wrong fraction of cats and dogs, it will be biased. And you can see this could have all kinds of consequences, which have lots of impact also on society. If you start labeling individuals with the wrong information, right? Or classifying their disease with the wrong information. I think this is a big question. Should you feed physics into the algorithm? After all, we like Newton's mechanics, we like GR. They've done extremely well, those theories. Why not telling the poor algorithm about them and look for deviation from them and in a way of learning physics? And there are different ways to interpret it. I've written here Bayes' theorem, which is now very much a common practice in cosmology of relating data and models, or in general, any variables A and B in terms of conditional probability rules. Now, here's a little exercise. I don't know if you can use the thumbs up switch on your Zoom, but if you can, I would really appreciate it. And I'll ask later, I cannot see it right now, but I'll ask later, Shona, if anyone put their thumb up to say that they can see simultaneously 12 dots here. Now, let me assure you, it's not an animation. It's not an animation, it's a static picture. You can print it, put it in the wall, and you'll see those black points jumping from one place to another. That's what my eyes see. Again, if anyone can see all 12, thumbs up. This is a limitation of the human brain. So usually the argument is, oh, we need computers, we need AI because we have lots of data. But it's not only that. Maybe a human could misclassify a galaxy, which is a tragedy by itself, if it says elliptical or spiral. But it's even more of a tragedy if a medical doctor may, try to identify a cancer cell wrongly, just because some optical illusion in a particular image. So this, I think, is another reason, is to appreciate the brain, but to help the brain. And a computer program can probably figure out those 12 dots quite easily. There are lots of open source now to do these things. In the early years, we always write codes from scratch. Luckily, there's a lot being developed now also in private companies, right? The free market there is very important, companies like DeepMind and so on. And you can see that this is a package called scikit-learn. There's a more advanced one called TensorFlow. And you can see all kinds of techniques. It's very small boxes there, but you can look it up on the web. There's classification, clustering, dimensionality reduction, and regression. Now in astronomy, we don't invent those algorithms, but I think we're quite good in using them and in collaborating with computer scientists, right? We are kind of doing the practical work, and they like to develop algorithms and see examples. So these are examples, only a subset which are highly biased towards work done in our group at UCL over the years. Galaxy type, star galaxy, supernovae 1A, classifying the light curves of supernovae, strong gravitational lensing, deep blending of images, photometric redshifts, finding masses of galaxies, and even searching for exoplanets and Planet 9 maybe, in data sets. And finally, of course, gravitational waves is a classic area where these methods are useful. And one can add many, many, many of those. I should say that I got interested in the early 90s. It seemed to me, perhaps naively, that, you know, how come individuals have to look at images after image and tell us whether it's a spiral or an elliptical. And we then had an exercise which ended up in this paper in Science, where we had 6 experts who classified the same images produced by the APM machine in Cambridge. Among them was the Vaucouleurs. This was actually his last paper, and Vandenberg and others. So we kind of immortalized knowledge of 6 experts, which was kind of a lot of fun, and seeing different patterns in how they classified. And you know, simultaneously, other people in particle physics. This is my UCL colleague, a particle physicist called Nikos Konstantidis, who's actually, he and I co-direct the CDT mentioned earlier, Center for Doctoral Training in Data Intensive Science. And he, in a parallel universe, used neural nets in the early 90s for particle physics. So clearly it started quite a while ago, but the big jump is now we've done more on this type of classifying galaxies, like galaxies. What you can see in this classification metrics, because we have the true answer from humans, that you can easily classify objects to well above 90%, even 96%. Then we also worked on photometric redshifts. This is many of these surveys I described, for example, DES and LSST and Euclid, they only look at the sky at different filters. For example, these are Sloan filters, GRIZ. So you don't see all the fine features in the spectrum you would get if you do spectroscopy, but you have broad photometry. And it's an inverse problem. Just by measuring 4 numbers, in some cases 5, could you tell the redshift? This is called photometric redshift. And I thought it's a problem for one afternoon, but I'm still working on it, and other people work on it 20 years later. It's quite challenging for many reasons, and it's critical for all these present surveys and future surveys. So we came up with a neural net solution. You put the magnitudes and you get the redshift. How do you do it? You train. Okay, you supervise the network based on a small subset where you know the true answer from spectroscopy. Let's say I have 10,000 with spectroscopy, and I can then present it with 1 million or 10 million or 1 billion. This is the idea. If you like to look at it in a more simple way, basically we write the redshift as a function of the magnitude. It's no more than a nonlinear mapping, but it's a clever mapping, okay? So we created a package called N and Z. Later we did another one, N and Z2, but really they're excellent competing packages now. There are a dozen or so techniques. Some of them use this learning from data approach, supervised learning, as we have done, and others use templates. And it's a very active area still, and they will see the fruits of it, obviously, with Euclid and LSST. One can take another step. You have the colors or the magnitudes in 4 or 5 or 6, or in some cases 30 bands. Why not learn more from it about the nature of galaxies, something like the stellar mass, the amount of mass in stars. And here, a current student of mine in the CDT, Center for Doctoral Training program at UCL, Sunil Mukesh, together with 2 former postdocs, is actually doing it simultaneously, not only the redshift, but also the stellar mass. And you can see here, stellar mass redshift. This is when you train on a shallow field. And here, that's where you train on deep field, which is of course better. And you can see by modality in the probability for where this tells me we don't know if the redshift is here or there. This one actually brought it to be 1. So I think there's a lot of prospects for that in this area. Now, there's a new game. Everything I showed you so far, we had the data compressed, right? We had few magnitudes, or we looked at the galaxy, we looked at few features of the galaxy, like bulk to disk ratio, the size, and so on. But the new area, which is developed very rapidly in machine learning, is so-called deep learning. And let me try to explain it. In the old approach, you can take a car and just make a little catalog. Each car, each object, you don't know it's a car yet. How many wheels has it got? What's the dimensions? And you feed those dozen parameters into a classifier. That's exactly what we did with the galaxies. But then in deep learning, you feed in the whole image of the car. Okay, that's the idea, the whole image. And this has been very active area. Now on the archive, I looked up across all fields in astronomy. It jumped from 23 papers 2017 to 83 in 2019. The numbers still go up for 2020. And you know, maybe at some point every paper will have deep learning in the title, so then people stop putting deep learning. But it's quite interesting. And you can think of it as a subset of machine learning, which is a subset of artificial intelligence. This is an example of these black boxes. Do we understand? And what you do, you take a picture of a bird, and there's a convolution. You convolve it with many, many filters that pick up features of different sizes, different shapes. Okay, so it's these filters which are convolved. The filters convolved with the original image that are fed into the next step. And then you know, is it a bird, a sunset, dog, or cat? So that's, you know, deep learning in 30 seconds, but it's a very important area. And it's been used, this is by a group, not our group, that used it on simulation of slope of LSST to look for arcs, right? I showed you these remarkable features of arcs due to gravitational lensing. You can see some arcs by eye very easily. Others are very faint. Those don't have arcs. And this computer algorithm seemed to have won. There was a competition, and this deep learning in a particular application called convolutional neural network seemed to have won, also over humans. Okay, it's won also over humans. Okay, so you've seen an example of deep learning. There is another problem that we're going to face in the next generation, and that's what are we going to do? This LSST is going to look so deep that images will start overlapping each other. Like these two, these are two separate galaxies, but how can we tell from one from the other? We cannot ask a PhD student to look at billions of images, right? So here is again some deep learning fancy algorithm that can actually, at the end of the day, can tell you that there are actually two objects there. Moving from one object, from galaxies to the ensemble, we would like to characterize the distribution. This is a simulation of dark halos, but we'd like to, it looks very much like the lambda CDM. It is lambda CDM, in fact. It looks very much like real data. But how can we tell it apart from a different universe, which looks like this, much sparser? Oddly enough, if you only do the 2-point correlation function, which most of the community does, they have exactly the same correlation function. Well, this was constructed cleverly to give that correlation function, but it shows you the risk if you look at that statistic. So here, a student who just finished, in fact, Krishna Naidu, just finished and moved to a postdoc, started a postdoc in Poland, used a technique called minimum spanning tree to actually look at that distribution. I pay tribute. One of the first people to use minimum spanning tree was John Barrow, who sadly just passed away. This is now a new incarnation of that, of how to do it, and to tell by other measures one from the other. But now, darkness visible, you know, the title of my talk, darkness visible, I borrowed from John Milton, the poet. And what you see here, I talked to you about weak lensing, is really a map reconstructed from the weak lensing measurements of the dark energy survey. Red regions show dense region. In fact, after you look at where the galaxies are in the survey, they're actually there. You know, many galaxies there. It's a dense region. So is this one. And blue region is kind of empty. It's a void. And you look at the distribution of galaxies, it's void. So light traces mass. But how exactly, we don't know. This comes under the name of biasing. Now the collaboration is working very hard on producing a map from 3 years of data. So this is the dark energy survey area in dark matter. This is a preliminary result, still what's called blinded, produced by my former PhD student, now a postdoc in Paris, Niall Jeffrey. You will see it eventually properly, so you have a preview of that. And it's superimposed, just to orient yourself on the sky, it's superimposed on a Gaia map, which has the Milky Way and large and small Magellanic clouds. But this is, again, another manifestation of dark matter. How do you do it? Here is, again, a deep learning approach. It's an inverse problem. You measure shear, you measure, and you want to find the mass distribution along the line of sight. There is something that does a transformation, a matrix A, and there is noise. And there's a classic, beautiful method which goes back to Kaiser and Squires 93, which gives you that picture if you apply to the dark energy stereo data. You've seen another version of it. You can use Wiener filter, which is an even older signal processing technique. And here is deep mass that Niall and others have developed, which is a deep learning process, and we're quite pleased with it. It makes use of simulations. So you throw in many, many simulations, and you teach the algorithm that when it would see the actual data, that's what should be the transformation from the measurement to the reconstructed property. I'm saying it very quickly, but you can look at the paper, look up for this. So we've taken yet another step, and that's to actually do something even more ambitious, to show a deep learning algorithm. This is a group in Paris, to show a deep learning algorithm, lots of simulations that come from different cosmological parameters, okay? So they've chosen, each dot here shows a simulation or ensemble with a particular omega matter, which we know in the real universe about 0.3, but they chose things which are much lower, 0.15 or so on, 0.45, and different clumpiness parameters, sigma 8, up and down. And they showed the algorithm, lots and lots of this, and they said, you know, they trained it to say, when the features look like that, you'll get omega m and sigma 8 like that, and some other parameters. And then they showed the real universe, and that's the blue contour here, which looks better than the red and orange here. This is using data from a survey called KIDS. Of course, the most impressive contour here is Planck, which does fantastically well. But as the areas of survey will go larger and larger, especially with Euclid LSST, I think we'll see more benefits from that. This is for reference, just a paper from the KIDS team that appeared in July, showing a similar story by more conventional methods. But no, we're quite excited. And there are a number of other papers I don't have time to go through that take that approach. So that's where we are, of really using simulations to do that. Another thing, and I'm conscious of the time, Emma, I want to show not just classification, but also dynamics. So, you know, we like to know the mass of the Earth. We live on the Earth. We like to know the mass of the Sun. We like to know the mass of the Milky Way. This is our galaxy. We like to know the mass of our neighbor Andromeda. As all of you probably know, we are falling towards Andromeda at about 100 kilometers per second. We'll hit Andromeda at some point. We might, those two spiral galaxies might turn into an elliptical galaxy in a dramatic merger. And can we tell the sum of their masses? Because people work pretty hard telling the mass of the Milky Way, telling the mass of M31. By the way, to within factors of 2. Okay, it's not that accurate at all. A fantastic measurement using rotation curves and other traces of the potential and Gaia data and so on. But we wanted to know if you take, can you constrain the sum of the masses? This goes back to timing argument and which was worked out 6 years ago, and then by people like Don Lynden-Bell, the late Don Lynden-Bell, a former, was a president of the RAS, who really was one of my mentors and has really influenced me specifically on this topic, and other ideas by Jim Peebles, who won the Nobel Prize in 2019 on this action. And then we did a little paper in 2017 led by a student called Michael McLeod on using machine learning, using again simulations to look at many pairs of galaxies, and then showing the data of infall, distance and velocity for our own pair and say, what's the mass? And now I want to show in a couple of minutes just the new incarnation of that. This is the story, how you use that simple dynamics to do it with references. And this is the new incarnation, a project led by postdoc of mine, Pablo Lemos, and I listed the rest of the cast. It's a paper which will be submitted very, very soon. So look for it on the archive in a week or so. The idea is now to use 2 million pairs of galaxies, 2 million, and then to ask, based on that, given the data we have of the distance and velocities, what is the mass of our own, the sum of M31 and the Milky Way? I hope you get the idea. The simplest algorithm would say, find it that among the 2 million, the one which is the most lookalike. But we do something more fancy using a package called Delphi from another group to actually look at the overall surface of probabilities connecting the mass to the velocities and distance. And of course, all that in a very strict Bayesian method and using also data from Gaia HST. To cut a long story short, this is the number to take home. We find 4.6 plus with that arrow bars, 10 to the 12 solar masses for the mass of the sum of M31 and the Milky Way. You can see the green line is our number with 68 confidence intervals. Blue is the mass of the Milky Way with 68 and 95%, and red is the M31. You see that we agree. It's at the lower end of the 1 sigma in that direction, but it gives a consistent answer. And by the way, for the experts, it's in units of M200. I already talked about it, that I'm really looking for something which is not AI, but augmented intelligence, that the technology, the cognitive technology can actually design to enhance human intelligence rather than replacing it. Hopefully, I presented examples of that. I would like, just like in the last slides, to talk about the next generation that has to be trained in a different way. It's not just about going to a telescope for 2 nights, but how do you cope with this data? So at UCL, with support from STFC, we started 4 years ago a Center for Data Intensive Science, CDT. There are, by the way, 7 other centers across the UK. We are the first to start it. And we have now 4 cohorts, in total 45 students. I've been fortunate to have 4 of them. You've seen the work of some of them, Konstantina on the H-naught from gravitational waves, and Sunil on the stellar mass redshift, and Ben, and I had no time to show his work, but he's just had a paper in the archive about looking at this data for transients, and especially kind of research for Planet 9 and similar things. You can look it on the archive. And Prab, who is at the bottom right, just started actually last week. So these are only 4 out of 45 who work on a range of topics. In this program, the students, it's a PhD program of 4 years. 3.5 years, they do a core astronomy project or particle physics project, but they have courses in computer science, and they also have experience doing group projects with companies. So we collaborate with these companies, and you see 20 or so them, Transport for London, the Met Office, some Alan Turing Institute, ASOS, and so on. And they also spend 6 months out of the 4 years working with them. And they come back, you know, they teach us about all kinds of new techniques, which go all the way from, you know, text recognition, understanding automatically emails, to actually Alzheimer's disease and COVID research. So, you know, a student after 4 years does not only cover lots of astronomy or particle physics, but lots of knowledge of something different. And I think it's great, and we're grateful for STFC, and I hope we can continue it, and I recommend it to other universities. Finally, we also have a spin-off that we thought, why not collaborating with the rest of the world? And we got a Newton Fund to work with Jordan. We got a grant from STFC and to work with Jordan. And unfortunately, we were planning all these lovely workshops to go and visit Petra and so on, but we have and you have to do it remotely. This was the launch event, another Zoom, but we've taught, there's a machine learning course that was created by a colleague, Jason McKeown. There are 45 students in Jordan, 62% female. Okay, so we're doing hopefully something good for the world in many, many ways here. And that's, again, something we would like to continue. Summary slide, Emma. Cosmology is no doubt going this industrial revolution in both spatial time domain with, lots of data coming our way, but there are challenges. So I'm not selling it as the theory of everything, the solution for everything. We need to think about what to do with incomplete training sets and how to augment them. We need to think about incorporating physics. We need to explain, interpret algorithms. We need to think about benchmarking, going to the exascale. We are part of a new program called BASE. Exa is 10 to the 18, right? Bytes and so on. We've illustrated it's a great training for PhDs and postdocs well beyond academia and astronomy. Will AI produce a better knowledge? Is going to be a new theory of physics coming from AI? Who knows? Depends on the data, depends in part on nature. Finally, really a big thank you to the RS for inviting me to give this talk, which has really made me think, on the bigger picture, but also credits to mentors, collaborators, postdoc PhD students over the years. And this is a picture from a conference we had, a year and a half ago, and it's quite hard to believe we could actually be together. We could be in the same building, and it looks like, like years, like long time ago. And I very much hope that, the future is bright, and post-COVID, whenever it's going to happen, we can have, again, meetings in person. But for the meantime, thanks very much for all of you who joined by Zoom. Sorry I cannot see you, but I'll be happy to answer questions, time permitting, and also to answer questions by email later. Thank you very much, Emma.
Professor Ofer Lahav, thank you so much for that wonderful lecture and for the insight into such an exciting topic and your significant contributions to this field. And it was really great to see you highlighting work from your students and postdocs and all the great messages in there about the applications of this work beyond the field of astronomy as well. Thank you so much. We do have time for some questions. So I'm going to hand over to Shona, Dr. Shona Urquhart, who's going to facilitate the Q&A session. So I've seen we've got some questions coming in. Thank you.
Hi, thanks Emma, and thank you Ofer. That really was a wonderful talk. And yes, we do have a few questions, so hopefully we'll try and get through as many of them as possible. So the first one I'm going to ask is, so congratulations on your award and thank you for a magnificent lecture. So the question that this is Roberto Trotta asks is, given the increasing complexity of our numerical and statistical approaches to cosmological data analysis, what role do you see for pen and paper theoretical cosmology for the future?
Well, thanks, Roberto, for the question. You're obviously one of the leaders in this field. I see a lot of room for paper and pen work, and I can explain it very quickly. In fact, I had a comment on a slide which I had no time to go through, so I'll do it now. With this approach of throwing, generating lots of simulations, there's one big limitation. How many simulations should you produce? Could you cover the entire parameter space of nature in any field? Could you do a simulation? What about magnetic fields, right? What about neutrinos in a particular model? So I think what we need to do is clearly design the simulations and show whether there's a need on simulations to do the next wave. And it's in fact, it's just what we've done in recent weeks with this Milky Way M31 project. We used the analytic model to tell us whether it's relevant to run more simulations, which not. And the answer was no. But that's the idea. Plus, I think, you can ask yourself a hypothetical question. Imagine there was no general relativity. You would give a machine learning all the data, or would it come up with general relativity? I doubt it. But maybe some are more optimistic. So I'm a great supporter of paper and pen, Roberto. Thank you.
Thank you. Right, we've got another question. We've got quite a few. So what really is dark energy? Do you think we can understand it fundamentally using current theories, or is it not likely till we have a fully fledged quantum description of gravitational phenomena?
Yeah, well, it's a big question.
Yeah.
And there are theoreticians who have thought about much deeper than me, but I'd say the following. First, the data currently indicate quite strongly that this W I showed is -1 plus -5%, give or take. Some of my colleagues think, well, maybe something is hidden in this 5%, the game is over, is lambda. In that case, it's a cosmological constant. Einstein's cosmological constant, just as the way it appears in relativity, just the way we've known it since 2017, except what is it? What is this lambda? Why has it got this strange value? When I was a student, it was believed to be 0. Now it has this strange, in certain units, 0.7. Why is it? There's a whole range of ideas. Maybe it's just like another constant of nature, just like big G. Some people think it's some manifestation of quantum fluctuations, vacuum energy, but there's a big embarrassment there because according to particle physics, it should have been much, much, much bigger by 10 to the power 120. So that's very embarrassing, actually, that it's so small. So we don't know, if you remember the Einstein's equation I showed, is left-hand side, right-hand side, that's part of the mystery. And some people, resort to entropic principle, for example, that we live in one of many, many universes that happens to have this particular set of constants. That's a very intriguing idea as well. I think your question is exactly what has attracted me and many other people to work on it, because what I like about it is these deep philosophical questions. We still don't know what it is, and yet in order to deal with it, you have to have kind of bread and butter. You have to work very hard, build instruments, develop software, do a careful job, and on that journey you learn new things. Okay, so although we designed and referred to dark energy, it also discovered a flash from a gravitational wave event. Okay, unexpected. So there are spin-offs, but I think the core question is still there, giving you some ideas. There's quite a lot in the literature about that.
Okay, so another one for you. Do you think that the current technology that we have is a hinder for the increasing complexity of physics?
Would you mind repeating it? It's quite a sophisticated question.
Yeah, it is. So I asked, is the current technology a hinder for the increasing complexity of physics?
Well, technology sometimes is ahead of the game, sometimes it's behind, okay? I think we have to, that's a general comment to make, especially for colleagues who are in the space research business. You plan something based on technology and the thing only starts working 10, 20 years later. Technology's moved on. What do? So you plan the next mission, right? So you do that. Even with ground-based, right? Things we started doing 15 years ago, we've seen only now coming to fruition. So I think you do the best you can. Of course, questions keep coming, right? And maybe what was sufficiently good to get accuracy of 5 or precision 5% is not good enough to get 1%. You need new technology. But I would also say that the good thing about this is the hardware side, but the good thing about the software side that you can still play with the data, and improve the algorithms along the way. Yeah.
Okay. Do you see augmented intelligence progressing to the point where it will give the result of a simulation from the input parameters, but without running the simulations? For example, the Millennium simulation.
Without running it, okay. So there is another area which I haven't quite covered. It comes under the emulation. What it is, I think, in other simple words, is interpolation. So what you can do is, instead of running the Millennium simulations for every, over a grid of hundreds of thousands of points, you want to change omega m, in very small intervals, which is very expensive. What you can do is, maybe I'm just making it up, but you get the idea. Imagine you can run it only 10 for 10 scenarios, and you can interpolate in between. And there's quite a range of papers in the literature doing exactly that. So you can use 10 simulations to create to create hundreds and millions of simulations which are based on those 10, but they're quite rich. Of course, you also have to be a bit careful about using too many fake universes, right? So you've probably seen examples. In fact, I just heard a talk yesterday by our CDT students about fake images. You may know there is a website called the website of people, the images of people that don't exist. So you can take people that exist and create images of people who are interpolation between, right? And some the people that never exist, right? They're just fake. But and now there is software that has to discover the fake. So when you run your 10 millennium simulations, you have to be careful that what you get in between is quite realistic. Thank you.
Okay, so somebody else asked, most of the limitations of machine learning you mentioned are related to insufficient training in the case of supervised learning. Couldn't these shortcomings be solved by using unsupervised learning algorithms like genetic algorithms?
Yeah, this is, I think, from the early days of machine learning, this is traditional. If you open a textbook, even from 20 years ago, you'll see there's supervised learning and unsupervised learning. And we all use them. I mean, a technique like principal component analysis, which is now very common, is an example of unsupervised learning. I tell nothing algorithm, and it might discover some features or nearest neighbors. Yes, I think all these are very important. And this is, again, in the context of augmented, I'll put it in the augmented intelligence language, that it's wonderful to show algorithms just the data as they are, let the data speak for themselves, and then come to the expert and say, oh, does it make sense to you that these galaxies actually form two different classes? A bit like blue galaxies, red galaxies, and the Green Valley, which is very topical. Does it make sense? And the astronomer may say, look, this doesn't make sense at all. It contradicts all the papers I've written the past 20 years, but actually, oh, the data actually show me something new here. And I think this is the way I think would be very nice to see the field evolving. Yeah, thanks for the question.
Okay, thank you so much, Ofer. That was, again, a wonderful lecture. And thank you so much for taking the time to answer the great questions coming in. Thanks to the audience as well for posting your questions. It's been a really good, interesting Q&A to have there. So as Ofer mentioned, if there are questions that we haven't had time to cover in the Q&A, then he will be he's willing to respond to some of those, which we will discuss with him about putting some answers on the website where the advert for the meeting is. So thank you for that, Ofer. Okay, so just to finish the meeting then, closing remarks for today, just to let you know that the next monthly A&G open meeting of the Society will be on Friday the 12th of November, again via Zoom. So look forward to seeing many of you again then. Thank you so much.